This is an example of how to solve problems 4 and 5 for the 25-26 academic year. Hopefully this will help you to solve any of these types of problems. Test the hypothesis that women who drink more than 24 ounces of water a day will have fewer days with UTIs than women in general, urinary tract infections. Women in general have an average of 17.9 days with UTIs. Sigma is 5.1. Xandra, who drank more than 24 ounces of water per day for most of her life, had a total of 6 UTIs in her lifetime. Use the significance level of 0.01 to test the hypothesis. So the first thing we do is parse the problem, and we're looking for the population of interest. In this case, it is women who drink more than 24 ounces of water. And who are we comparing them to? We're comparing women with women, women in general. This is how we'll be stating the hypotheses for the first few tests that we're doing. What is it that we're measuring? We're measuring the number of days with UTI infections. So I'm going to write days with UTI. And infection is part of the word, so I won't write out the word infection. Days with urinary tract infections. For the tails, we're looking for a directional word. Scanning the problem, I see this word fewer. And so that word fewer gives us an indication that we're doing a one-tailed low test. Our research hypothesis then is that population 1 will have fewer UTI days, than population 2. That's our research hypothesis. And our null hypothesis, I'm just going to copy and paste, and I'm going to add this word not. And that's how we'll state these hypotheses. And we'll leave it at that. Our next step, step 2, is to describe the comparison distribution. So what is typical for women? Well, we know the center of this distribution, mu, is stated in the problem, an average of 17.9 days. So mu equals 17.9. I'm actually not going to write it out that way. I'm just going to write the 17.9 because then I can use it in a calculation. The spread is also given in the problem. We're using n of 1, so we use the spread just like it is. It's 5.1. And in this case, we always assume the shape is normal. And so this distribution here will be applicable, and we can use it to draw on. Alpha, the significance level that the researcher has chosen, is stated in the problem always, and it says alpha is 0.01. So we're looking for only 1% error. The researcher has a strict standard, and the cutoff point, Z alpha, we have to look up. We can look it up using one of two tools. We could use this tool and look for alpha 0.01 by dragging this over and waiting until we see the 0.01 down here on the area to the right of the distribution and see what score appears. This is a little bit trickier way to do it because it's hard to get precise. And so we generally use a different tool that is for you on your left menu. It is called the Z cutoff calculator, and I'm pulling mine up right now, the Z critical value calculator. And for this case, all we have to do is put our alpha in, and we can calculate, and it tells us, we're using alpha of 0.01, the critical value of Z, or Z alpha, or the cutoff point in a one-tailed, a right-tailed test would be 2.33. We have a left-tailed test. This would be a minus 2.33. We just add the negative sign. The critical value, or the cutoff point, or Z alpha, in a one-tailed low test using alpha 0.01 is going to be minus 2.33. Let's go ahead and write that in, minus 2.33. And at this juncture, we can also plot it. I like to use my pen because I have it, but I know that not all of you have a pen, so you can use insert inserting lines and shapes to do this just the same. For our example, I am going to use our pen. Our cutoff point is minus 2.33, which would fall right about here. I'm marking it in red. And we are looking, because it's one-tailed low, we're looking for a lower score. We're looking for a score in here. This table of the distribution. Again, you can insert shapes to do this. I'm going to write Z alpha, that's our cutoff point, is minus 2.33. So we're going to need a score that's lower than minus 2.33 if we want to reject the null and have a significant test. So we remember that always in this region is the fail to reject the null. That means the null hypothesis stands. And if we have a score in this lower tail, we have a happy researcher because we have rejected each other. If it's in the shaded region. Okay, next step is to find the sample z-score. We know that the formula for z is each individual score minus mu, minus the sample mean, minus the population mean divided by sigma, the population standard deviation of the spread. And so now we can just type this in as a formula. So we have our raw score given in the problem. Zandra, who drank all this water, had 6 UTIs. So let's write first equals 6. That's our sample score. Minus 17.9. I'll just click in that cell. And we'll divide by sigma to get a z-score. Oh my goodness, very close. Minus 2.333333. So it's just right on top of the score that we're looking for. I'm going to indicate it right here. It is just barely to the left. That's z sample equals minus 2.333, just a wee bit in that shaded region, but a wee bit is enough. It falls within the shaded region. That allows us to reject HO, and we conclude that taking and getting we can cross off the null hypothesis. Oh, it's gone. We can take our research hypothesis and just turn it into a sensible statement. People, women who drink more than 24 ounces of water per day. And I'm going to go ahead and grab some of this and put it in the next line. I don't need the word will. I'm no longer predicting. We do say we add the word significantly because we've just done a significant test, and just moving this to the next line. Then women in general. And now we put the statistic Z equals minus 2.333. I'm going to add the 3 so that it's clear. And the probability of getting that score, or the significance level we tested that, is less than 1%. We just put alpha there. We don't have to look up the actual percent. And so this is the conclusion. The population 1, women who drink more than 24 ounces of water per day. Next, we say they have, and we add this word significantly, fewer UTI days. What do we measure? Than women in general. Then in parentheses, we tell what test we did. We state the statistic, and we tell the probability.